Hi everyone. This video is going to be me going over Conway's Criterion from section 5.2, and then I'm also going to be covering section 5.3, which deals with non-periodic tilings. So last time we saw periodic tilings that you can copy or basically move the entire tiling pattern over, and you'll get an exact copy of that same tiling pattern. Non-periodic tiling is going to be the case where you can't do that. So in this video, the first one, I'm going to be going over all the content for it. And then in the next video, I'm just going to go through a whole bunch of examples from quiz 12. So including a lot of true false ones where I can explain why I get a particular answer. Okay, but to start off, I'm going to continue talking about Conway's Criterion. So we saw last time when I talked about Conway's Criterion, I was focusing on this rotational symmetry. Okay? This idea that if I took a triangle, for example, and I wanted to tile the plane with that one, we know that it tiles the plane just because it's a triangle, but it fits really nicely because all these straight edges can be rotated 180 degrees and we'll get that same shape back. This shape here, I copied and pasted and then rotated 180 degrees as well. So we can see even curved shapes like this are also able to be rotated as long as they have this point of symmetry, right? This rotational point of symmetry. Okay, so you may or may not have seen this discussion of what an opposite side is on there, so I wanted to talk a little bit about that as well. And this only applies, notice this only applies for 5 or 6 pieces. So looking at the shape over on the left here, let's say that this is one piece is each side of this pentagon here. So this is a 5-piece shape. If I want to talk about the one that's opposite to this one, I actually have 2 options. It's either going to be this shape, or sorry, this piece over here, or this piece over here, right? For 5-piece ones, it's right. So for 5-piece ones, it's whatever is not touching that piece, right? So this would not be opposite, this would not be opposite, but either of the 2 ones up here, right? Those are good. These ones, right, not opposite to it. For a 6-piece one, so I've got a couple 6-piece shapes here. If you take each of these shapes here to be one side per piece on here, let's say I wanted to look at this side right here. Actually, I'll use the same color scheme here. Right. If I want to find the opposite side of this, there's only one answer for this one, right? This is the only side that's going to be, or the only piece that's going to be opposite. And right, these ones are not going to work out. What may be not super intuitive is if I look at this other 6-piece one, if I asked, just a general population, what's the opposite side to this piece over here? A lot of them would pick this side over here because it's on the opposite side. But our definition for opposite in 6-piece shapes is, notice here that we're counting 1, 2 pieces over on this side and 1, 2 pieces over on this side. So we want to achieve that same balance regardless of how big the pieces are. So I could count 1, 2 pieces over here and 1, 2 pieces over here. So it turns out this is actually the opposite side over here, right? So Right, that is our opposite side over there. For a 5-piece, again, it's you can have 1 or 2 on either side of it as long as it's not touching. But for 6 pieces, we need to have 2 pieces on each side. Okay, so I want to look at a shape like this. Kind of talk about breaking this up a little bit on here. This shape, as it stands right now, well, sorry, I'll save that one for last. Okay. This shape here, so I've already broken it down into 1, 2, 3, 4, 5 pieces here. The next topic that I want to cover is this idea that they are translates of each other. So we see that a couple spots in this Conway's Criterion. But when I made this shape, I took this purple piece here and I just copied and pasted that purple piece and put it over on this side of it. So we would say that these 2 purple sides are direct translates of each other. I didn't rotate them at all. I didn't mirror them. There's no reflection happening on there. I just moved the piece exactly as it was from one spot to another. So this shape here actually does satisfy Conway's Criterion, right? As it stands, I've got 2 pieces that are on opposite sides, right? So in a 5-piece, these are on opposite sides. And then every other piece has rotational symmetry. This piece has rotational symmetry because it's a straight line. This piece as well. And even that curvy piece, we saw that we can flip that over, right? And that will fit back into the shape like that, right? So yeah, this one satisfies everything in Conway's Criterion. It's 5 pieces. The opposite sides are direct translates of each other, and all the remaining pieces have rotational symmetry. Same thing with this one over here. So if I didn't highlight these pieces, you might sort of think that each of these pieces here is not a direct translate, these pieces don't have rotational symmetry, and you'd be right? If I took this piece here, right? If I took the whole thing, I understand why it does that. It's very frustrating. This yellow piece here does not have rotational symmetry, right? If I take this shape, let's see if I can just get it to look like this. Here we go. All right. If I take this piece, right, that's supposedly satisfying Conway's Criterion, that is not going to have rotational symmetry, right? If I rotate it 180 degrees, it doesn't fit back in. So this shape still satisfies Conway's Criterion, right? Reading it from start to finish, it's made up of 3, 4, 5, or 6 pieces. Okay, this one's made up of 5. If the shape is 5 or 6 pieces, 2 pieces on opposite sides are direct translates of each other. These 2 pieces, I just copied and pasted them so they fit into each other. So that's taken care of. Give it one more shot. Weird. So if I take this piece, since it's just copied and pasted, this shape will fit in just like a jigsaw puzzle, right? I can take this shape over here and it'll fit back into this shape here perfectly. So for that reason, all the remaining pieces that are not translates of each other have rotational symmetry. So we don't need to worry about these two pieces that were translates of each other on opposite sides. Those don't count for needing rotational symmetry, but everything else does. Okay. One more quick example. So let's say I take 1, 2, 3, 4, and then I'm going to take this shape over here, 5, and then 6 over here. So in case you missed it, I copied this piece over here and I pasted it over here. Okay. So these two pieces are direct translates of each other, but if I break it up in sort of the expected way, right, where the rest of these are just the one side per piece, this is a 1, 2, 3, 4, 5, 6 piece shape. So 6 is an acceptable number, but remember that these translate pieces need to be on opposite sides, and they're currently not on the opposite side of each other. Right? Now, this doesn't mean that there's no way for the shape to satisfy Conway's criterion, but in its current state, right? If I asked you, "Hey, I broke this up into pieces like this. Is this okay?" The answer is no. It's not okay because these two pieces that are direct translates of each other are not on opposite sides. Now, if I just gave you the shape, right, the plain shape without any markings on it, you could start to experiment a little bit with, well, these two pieces are direct translates of each other, but maybe this piece sort of seems like it has maybe a shape that could have rotational symmetry. In which case you could break it up into 4 pieces. You could also call this 1, 2 pieces. So maybe that's allowed, right? That is allowed. So maybe that'll help you get 1, 2 pieces over here, and maybe you could call this 1, 2 pieces over here, but we're still running into issues, right? This purple piece doesn't have rotational symmetry. But the point is that if they give you the pieces, right, they're showing you the pieces, you need to take those pieces exactly as they are. If they just give you the shape, there's a lot of flexibility into how you can rearrange them. So I'll show you that in the next video where I go over some examples, but just kind of be aware that that's something you might want to watch out for. Okay, so that was Conway's criterion. The next section here is going to be about non-periodic tilings. So every tiling that we've seen so far has been what we call a periodic tiling. If I take that tiling and I move it to a different spot on there, I'm going to get the exact same tiling back. That pattern repeats itself over and over again, and so I can get that same pattern back. This pattern, this is called a Penrose tiling. So this is a picture from your book. There's a lot of different variations of this, but this is called a Penrose tiling. And what we can notice about this is, let's say that I find a good color for this. This pattern only made up of 2 shapes, right? It's made up of these red, what we call darts, and these teal kites. But those darts and kites, those are the only 2 shapes that make this up, and we can continue this pattern forever and ever, right? You might recognize this from paper towels, right? Sometimes they have this sort of pattern perforation on them. But let's say I want to look at let's say I suspect that there's some kind of like repeating pattern on here. So I want to take this star and let's say it's kind of pointing in this direction. So I'm going to move it down here. All right, it's going to look like that same star over here. I think that I can recreate that pattern. If I look at all the stuff around it, this piece right next to it does not translate to this piece next to it as well, right? And you'll see that anytime you try to move one, small pattern to overlap another small pattern, you're going to get something different about it, right? So this, whenever they're asking you about something that's a non-periodic tiling, this is the only one. Sorry, it's a tiling, but it's a non-periodic tiling. All right. So as far as this class is concerned, this is the only non-periodic tiling that we're interested in, right? If you want to see how it's formed on here, you can see those same dart and kite shapes over here, but there's some curves that kind of form complete loops on here in some interesting ways. So if you look through the darts and kites, you can kind of trace these intricate curving patterns on there, but the idea is that they just never repeat each other, right? Okay, so that's not all you need to know about this non-periodic tiling. We want to see how we make these shapes, because these are a very specific shape here, this dart and this kite here. So we'll ask the question, what forms a Penrose tiling? And they actually come from the golden triangles that we saw earlier. So remember, these are a type 1 and a type 2 golden triangle. If I, underneath this type 1 golden triangle, if I make two Sorry, I'm gonna right. So there's a type 1 golden triangle, and I copy and paste that, and then flip it. Like this. If I put together two golden type 1 triangles, this is what forms what's called a Penrose kite. So Penrose kite would be two type 1 golden triangles. Right, so that's a Penrose kite. That's what makes up these blue shapes over here. The other one, a Penrose dart, is going to be made up of two type 2 there we go. Two type 2 golden triangles. So I'll draw one like this. Here's a type 2 golden triangle. And then if I do the same sort of trick where I flip it like that, I can get a what's called a Penrose dart. And that's going to be made up of two type 2. Golden triangles. So the types of questions that they'll commonly ask you are to figure out, they'll say, hey, what's the area of this Penrose kite or this Penrose dart? So that's just an extension of what we did with the golden triangles, finding the area. For this one, I'll go ahead and copy these two entities. We'll call this finding the area. Right. Finding the area, I would say just break this up into two right triangles, right? And then here's a 3, 4 right triangles, right? Just like you would find the area of a golden triangle by breaking it up into two right triangles. This is just 4 of those golden triangles. Right, same thing here. We've got 1, 2, 3, 4 right triangles. One last thing from this section, and it's actually something that we didn't quite talk about in the golden triangle section, but they do ask about this. So if I look at this type 1 triangle and I make a diamond shape like that, or if I take this type 2 and I make a diamond shape like that, let's say these are both called golden diamonds. Right, so here's a type 1, here's a type 1, here's a type 2, here's a type 2. Okay. So, yeah, we'll look at finding an example of finding the area of these, and we'll go over some seeing if we can figure out whether shapes satisfy Conway's criterion in the next video, where I go over these examples here.